Yeah, I also don't have an option to record.
Yeah, I don't see an option either.
How come you see an option, John? It's so strange.
That's the
No idea.
Okay.
perks of being John Langford.
Good morning, guys.
Hi, Harish.
Morning.
So I think 11:02. Let's give it one more minute, see if more people will join. Hey, Jack, can you ping some of our folks?
Yeah, we'll do.
So Peter and Pivot right here. Okay, I'm gonna start because otherwise everything will be delayed. So thank you everybody for attending our reinforcement learning summer festival, whatever we decided to call it. But we have welcomed this year for the first time a great bunch of students that have joined us to work on our online machine learning interactive system. And they came from across the world. We're so happy to have had you, all of you, come and join us. And we're so excited about the work that you have all been able to accomplish. And this is a new program that we are actually just trying out for the first time. So we're excited to see all the work that has been done, and we're looking forward to seeing you present to across the labs here in the Northeast, as well as some visitors from our product team that are going to come and join us. John, did you want to add a few welcoming thoughts here before we kick it off?
I don't think I have much to add. I'm great looking forward to the presentations.
Excellent. Just a quick thank you for some key people that made this RLOS work this summer. Jessica, who has been working behind the scenes for multiple months before we started, and Jack and Rodrigo, who are part of the organizing committee. So thank you for doing this. And without any delay, why don't we kick it off? Jack is going to be our master of ceremony here. So Jack, maybe you can kick it off and just make sure that people are landing on time so that we don't delay things.
Yeah, thanks, Rafa. So first up, so everyone has 15 minutes to present and then 5 minutes for Q&A. So at 10 minutes into the presentation, I'll just give you a little heads up. We do have a pretty packed schedule, so I will keep to that. And if we have any time left over at the end, we can come back to questions or something like that. So first up, we have Newton. So he was mentored mainly by Pavithra. Take it away, Newton. Thank you.
Can you see my screen?
Yeah, looks good.
Okay. Hello, everybody, and thanks for coming today. My name is Newton Mwai, and I've been working on the project titled A Library of Contextual Bandits Estimators. My mentor has been Pavithra Srinath, and through her I also met Miro, Akshay, Adith, and Jack, who also provided great direction for this project that I am grateful for. A little bit about my own background. I am from Nairobi, Kenya, and the picture that you see on your screen is a picture of a southern white rhino and its calf with the Nairobi skyline in the background. So feel free and feel welcome to visit Nairobi. You will have a good time. I am an alum of Carnegie Mellon University Africa in Rwanda. I graduated in May with a Master's of Science in Electrical and Computer Engineering. and I just started my PhD in computer science and engineering at Chalmers University of Technology in Sweden this August. So my presentation is structured as follows. I'll start with a brief introduction of policy evaluation and estimators, and then I'll talk about the specific project goals before presenting a report on the project, and then I'll take you through a demo of the code before concluding with my experience and takeaways and taking your questions. So let's start with the policy evaluation. In a policy evaluation, we aspire to answer the question, what if? Which means that this is a counterfactual evaluation problem. And how we proceed with a policy evaluation is as follows. So we run an experiment with randomization to generate data that saves the context, the chosen action, the rewards and probabilities of choosing the action. The policy that was run is referred to as the logging policy. And we are curious about how well another policy referred to as a target policy will perform under the same setting. So estimators give us unbiased estimates of the performance of target policies. So why is policy evaluation important? First, in the real world, decision-making problems in healthcare, finance, robotics, and marketing, deploying a policy without having an accurate estimate of its performance could be costly, it could be unethical, or it could be illegal. So policy evaluation gives us a way to circumnavigate these challenges. Another thing is that policy evaluation also allows testing a large number of candidate policies than will be possible by online A/B testing, which is another way of assessing candidate policies. In this project, we extend the estimators library and implement an interface to help researchers and data scientists to test different estimators quickly and easily. So a brief about estimators. Estimators are used to estimate the value, which is the expected reward, of a target policy using data collected under a different policy, which is the logging policy. Examples of estimators include the IPS, W-robust, and pseudo-inverse. So one thing to note here is that these estimators perform better or worse in different settings. So you may want to test if which estimator works best in your setting. In this project, we explore estimators, reference implementation, and allow for comparison to aid in understanding and selection. So this is how the current estimators library looks. We have a number of estimators that have been implemented, including the MLE, the IPS, Cressy-Reid, and recently the pseudo-inverse. So in our project, we'll be extending these estimators library and also providing an interface for comparison and evaluation of estimators. Specifically, our project goals are as follows. So we wanted to add an implementation of W-robust and W-robust in episodic settings to the estimators library. We also wanted to implement a simulator interface that allows for evaluation of target policy against logging policy. We wanted to add support for custom VOPA policies. And another major one is that we wanted to generate random logging policies and target policies to use for estimators evaluation. So how you do this is you transform a supervised dataset into a contextual bandit dataset, but we also had the constraint that we wanted to do this by enabling the user to provide custom soft-training parameters. So soft-training enables you to transform a deterministic policy into a stochastic policy. So we wanted to enable the user to provide custom soft-training parameters. We also wanted to do visualization of the comparison. We also had a couple of stretch goals, including implementation of pseudo-inverse and integrating into the existing counterfactual evaluation framework. So regarding our achievements, we were able to achieve all the points in the goals to completion or to near completion. And as for the stretch goals, the pseudo-inverse had a pull request for a while, I think from Jack, and it was recently merged with the estimators library, so we will need to re-implement it. But as for integrating into the counterfactual evaluation framework, we weren't able to look at it given time constraints. So now I will head over to a demo of the code. I will start with the estimators. These are the estimators, again, as I had mentioned, that have been implemented and the ones that we've added. We also added a few modules to help us in our comparisons and evaluation. The first one is the evaluation module, which provides an interface for interacting with the implemented estimators, and it provides for evaluating the expected reward, comparing performance of estimators and other related tasks. We also have another module called softening, which provides functionalities related to softening and transforming a classification dataset into a contextual bandit dataset. And we have another one called policy, which provides capabilities for invoking policies, including the custom VW policies. So let's start with evaluation and comparison. So a few things to note here is that policies and estimators will be provided as strings as specified, for example, constant for a policy and dr batch for an estimator. And in this section, we use DAM, quote unquote, policies. These are constant and uniform random. So constant returns the same action from the set of available actions, and the uniform random samples the available actions uniformly. So to evaluate the value of a policy given an estimator and the logging data, you just pass these to a function called estimator. Compute estimates, and it gives you the expected reward, and it also visualizes for you the change in the expected reward across the samples. So in another one, you provide the policy that you want to evaluate, the estimator, and the logging policy. The logging data to the compute estimate, and it does the same for you. It computes the expected reward and visualizes. So we have DR online and DR batch, and just to mention briefly, so in W-robust methods, we have something called the reward predictor, and in DR batch, you train the reward predictor with a batch of data. So you train a model once and predict on the samples using the model that has been trained. But for online, you update the reward predictor as you see the samples. So that is the distinction between DR online and DR batch. We also added support to train the reward predictor using scikit. So if someone wants to train using scikit, they can do that for the reward predictor. So this is just visualization of the same from the reward predictors trained with scikit. Now, in the previous section, we used constant and uniform random as our policy. And in this section, we show you how to use overloaded policies. For example, if you have a policy like this one, we'll pass the policy the same way we did in the previous section. So for example, we pass it as custom VW policy and the policy string, and we pass an estimator and the logging data, and it computes for you the expected reward as initially. This is another policy. It does the same, and this is another one also. So you may want to compare various estimators on one policy. So here we pass a list of estimators, and we want to compare how they work on this policy called constant. So you pass it to a function called compare, and it does that for you. So it gives you a report and also gives you a visualization.
You have 5 minutes remaining.
Okay, thanks.
Yeah.
So here we want to evaluate performance of several policies on one estimator. So you pass the same to the compare function, and it does that for you. It evaluates, gives you a report, and also gives you a visualization. Here you want to compare several policies and several estimators. So it does the same and gives you a good visualization of the comparison. Now, in generating a contextual bandit dataset, you start by training a deterministic policy, which is basically, for example, in this case, you just have a classifier model. So once you've trained the classifier model, it becomes our deterministic policy. Once you have the deterministic policy, you do something called softening. And softening, again, is a method for transforming deterministic policy into a stochastic policy. Here we will be supporting 3 different softening methods. The first one is neutral, another one is friendly, and another one is adversarial. And these perform as their name suggests. So in neutral, it just does a uniform random sample from the available actions. And for friendly, it tries to return the same actions from the deterministic policy with some stochasticity. And for adversarial, it tries to return different actions from the ones given by the deterministic policy with some stochasticity. So you expect that if you use some metrics, for example, cosine distance, to evaluate how these softening methods work, you expect to see that friendly will have a small distance between the actions given by the friendly softening to the deterministic policy, and neutral and adversarial should have a larger distance if you use cosine distance as your evaluation metric. And this is what we are showing here, and it is exactly what is happening. Now that you can do softening, you want now to generate a logging policy and a target policy, and in this section we'll be calling them behavioral. So a logging policy will be called behavioral policy, and an evaluation policy will be called, and a target policy will be called an evaluation policy. So once you have the logging policy and your target policy, now you can be able to evaluate your estimators. So here, for example, we generate a behavioral policy using custom softening parameters. So this is what we are doing here. We pass custom softening parameters to generate a behavioral policy. We also generate several evaluation policies. And now we'll be able to evaluate an estimator using these combinations. For example, evaluating some evaluation policy on some behavioral policy using the DR online, it gives us an expected reward. And now, since you know the ground truth, you can be able to evaluate the performance of your estimator using metrics such as mean squared error, which is what we are doing here. Let me go back to the presentation and wind up. So my takeaway and experience, I got a rare opportunity to learn about policy evaluation, which has broadened my scope of thinking for related research problems. I met and worked with amazing people at Microsoft Research, including my mentor, Pavitra, who has been a great mentor, and I really enjoyed working with her. And this has enabled me to do good work. I really enjoyed working with her, and I'm grateful for that. I also got an opportunity to interact with world-class researchers at Microsoft Research, whose work I admire. And I'm grateful for the opportunity, and I hope to continue using and contributing to global orbit in my research. So that's it for me. I'll be happy to take and answer your questions if you have any questions.
So I don't have a question, more of a thought. There's these variants of double robust called more robust double robust. Have you done any experiments with these variants?
No, we haven't done any. We haven't implemented any variants, including more robust. Maybe we'll do that as we. I hope to continue working on these. I can dedicate some few hours to continue working on this. Probably I can do that then.
So I think a good experimental evaluation of the more robust double robust might change the way we actually use the double robust learning as well as the valuation, and that could have a broader impact.
Okay, thanks.
Oh, and Newton, there's one thing I just wanted to add. So in the softening, you can also like customize your stochasticity. Your library supports for that as well, right?
Yeah.
Yeah, cool.
All right, I'll hand over to Jack.
Thank you, Newton. If anyone has any more questions, feel free to jump in now. Otherwise, we'll move on to the next presentation. Cool. Thank you so much, Newton, for presenting that. It was great. So next up, we have Cassandra. She's been working with Peter on the Parallelized Parsing project. So feel free to take it away.
Can everyone see my screen?
Yep.
Great. Okay, so this summer I worked on the Parallelized Parsing project, for which I multi-threaded the parser component of VW and separated out the reading of input into its own thread. My mentor for the summer was Peter. So to introduce myself, I'm Cassandra. I'm a rising junior at Columbia studying math and CS. I'm currently living in Connecticut, and a fun fact is that I play the cello. To go into some motivations for this project, so our first and primary motivation is performance. So VW is known for being a very fast ML system, and the parse thread is currently a bottleneck that runs with more than one order of magnitude slower than the learner. So if we can multi-thread the parser and reduce this bottleneck, VW will be even better at what it does. And we can also better utilize resources by using resources in parallel or making them more efficiently available to other parts of the code, like the learner thread. A secondary motivation is good design. So multi-threading the parser is going to separate out independent parsing processes, and it also gives the user more choice. So they can more flexibly use VW by choosing a number of threads, and they therefore have more options. So for the project goals, our first goal was to separate out the IO thread from the parse threads. So the primary reason this is our first goal is it's a necessary step in multi-threading the parser, since the reading of input needs to remain single-threaded since file IO is not thread safe. But this also has other benefits for modularizing our code, so having a small and clear interface between components, and also performance benefits because things are happening in parallel. So to accomplish this first goal, first we'll need to spawn a thread for reading different types of input. So currently in VW, we have text input, JSON input, and cache input. So text and JSON are ASCII input, and they have end-of-line delimiters, so we can read line by line. But for cache input, this is a binary format, so we can't use these end-of-line delimiters and need a different sort of structure for reading an input. We'll also need to have a shared data structure between the IO thread and the parse threads that's going to contain our lines of input. So we'll add to them from one thread and read from the other. So for our second and main goal, we have multi-threading the parser component. So as we mentioned before, the primary benefit of this is going to be performance, which I'll go into later. And we also have a secondary benefit of some good design and modularization. So to accomplish this second goal, we'll first need to spawn threads for parse jobs. So the user is going to specify the number of threads they want to use on the command line, and we'll spawn the corresponding number of threads. We'll also need to ensure that there's extra structure in place for communicating between the different threads in terms of waiting for different processes to finish up, or reading from and writing to data structures on different threads. And lastly, we want to ensure that the original ordering in the data file is preserved. So now we're going to focus on the step, since it's a step that we needed to think carefully about in terms of design and implementation. So I'll go through an animation of how example ordering is maintained. So here is our setup. We're supposing that our IO thread at this point has already added 4 lines of input to the IO lines queue. We have an empty example queue at this point since it's the start, and we're supposing that the user specified that they should use 2 parse threads for their VW implementation. So the first step is going to be for one of the parse threads to get the first line of input to parse. So atomically, as the IO lines, as we pop a line from the IO lines, we're going to add an example to our example queue, essentially reserving a slot in the example queue so we have the correct ordering. And we're going to do the same thing for our second line of input to parse. So we pop a line from the IO lines and atomically reserve a slot in the example queue. So now the learner at some point is going to want to get an example. So it pops an example from the example queue, and it's going to wait now until this example turns green in the animation, which indicates that it's parsed. So let's suppose that the parser thread controlling example 2, which corresponds to the second line of input, finishes parsing. At this point, the learner thread is still going to wait on example 1, since we need to read and use the examples in order. And once parser thread 1 finishes parsing example 1, our learner can learn with example 1. And then, since we already did the work in parallel of parsing our second line of input into an example, this example 2 is already complete, and we can learn with it right away. So we save some time, and this is an efficient process. So that's how example ordering is preserved. Now to move on to a before and after flow for VW. So here's a picture of the before flow for VW. So as you can see, we have an input file, and the parser contains the processing IO component. So we read in lines of input in the parser, then parse those to example. And then once we parse these lines to examples, we add them to the example queue for the ML engine to use. In the after picture, now we have at least one more thread if no additional parse threads are specified. This additional thread is going to be the processing IO thread, since we need to keep the processing of IO single-threaded since file IO is not thread safe. So we have a first thread which takes the lines of input and adds them to an input queue. In parallel, for however many parsers are specified, we take lines from this input queue and we reserve slots on the example queue and essentially pass over parsed examples to our ML engine. So now I'm going to briefly go over some detailed diagrams for how this exactly works. So let's first focus on this part here, which is processing IO, sending it to a queue, and having multiple parsers parse these lines. So for separating out IO, so on our IO thread, we're going to iterate through our input file and read lines of input and add them to our input queue. Great. And then on our parse thread, while we're not done parsing through all of the input, we wait until we have input to read from our input queue. We pop a line and we parse it to an example, and we continue to do this for all the lines of input. For our second component here, the parser and learner interaction, we have multiple parse threads, so the user specifies the number of parse threads on the command line using the num parse threads option, and then we create a vector of parse threads corresponding to this number. And for each of these, we atomically get a line of input and push it to our example and push an unparsed example to our examples queue, as we saw with our animation before. And then we go through the process of converting this line of input to an example. Once our example is parsed, on our parse thread, at some point we're going to have a function where we need to process examples. So we'll want to pop an example from the examples queue. But now before using this example, we'll have to wait until we're notified that it's parsed. So there's going to be additional waiting here to ensure that examples are only used when parsed and they're used in the correct order. Now for remaining work. So for this project, the goal was essentially to demonstrate that the multi-threaded parser would work for text input. So that was our focus. So some of the work of ensuring that our project is a fully realized implementation and works for other input types and specifications was out of the scope of the project. So we'd need some additional work before being merged to the master VW branch. So first, we'd need to make sure that all three input types are working efficiently. So the focus of this project was on text input, making sure it works and is efficient. But we need to make sure cache input and JSON input works efficiently as well. So cache input as of now works in a single threaded format because of some of the complications that come with binary input, but it's not yet efficient. And JSON input was not in the scope of this project, so it's not yet supported. Also for remaining work, and this will be tied into performance, which we'll go over soon, we'll need to or want to use the original VW code for one thread. And this is because at one thread, the VW code for this project is slower than the original. This is because our design changes introduced additional steps. But if we're using one parse thread, we haven't yet utilized the benefits of multi-threading that balance out the time of the additional steps. So now I'll go over a demo of a text file example with about 1 million lines of example of input. Okay, so here's my command line. I'm first going to run the baseline VW code that I did not modify. So we see that this ran in 3.236 seconds. Now I'm going to run VW, my modified code, with one parse thread. So first, I want you to notice that now we have a new command line option, which is great. Second, I want you to notice that the output is the same. And third, I want you to notice that for this thread, we run in with one or so more seconds, which we are expecting for one parse thread. Now for 5 parse threads, we run this code, and we have a real time of around 3.049 seconds, and we see the same output. And 3.049 seconds is around the same amount of time as the baseline VW code. And then let's run it with
5 minutes left.
Okay. And then for 8 parse threads, we see an improvement in performance, which is great. So I'll now show you what this performance looks like in a chart. So I plotted performance. So I ran VW 4 times on our 1 million line of input example. And I took the average over these 4 times and plotted it for the different specifications. We expect that if we plotted this over more sample runs, we'd see a more natural looking curve. So as mentioned before, we're going to have an increase in time for one thread since our process is adding additional steps, but we're not yet using the benefit of multiple parse threads. Now for 3 to 6 threads, we run in approximately the same time as the original VW code, and we have an improved design, which is great. And finally, for 7 to 10 threads, we're running in 66% time of the original VW code, which is a 34% improvement in performance. So this is a great indication that multi-threading the parser could be something really useful and help VW's performance in the future if integrated into the master VW code. Great. So now to wrap up the presentation, I'm going to go into some of the things I've learned throughout this project. So first, for some technical learnings, I came into this project with some experience in C++, but I really grew at my ability to use C++ in a more professional quality setting, and I improved in my understanding of some of the fundamental concepts in C++. Second, I really grew in my understanding of how multi-threading works. So I learned how to use the C++11 threading functions, and my mentor helped me understand more about condition variables, locks, mutexes, weighting, and how multi-threading has a ton of benefits, but also a lot of challenges that come along with it. I also learned how to debug using tools like GDB, and I learned about some of the resources that exist for debugging multi-threaded code and locks and mutexes, and I understood some of the difficulties of creating these tools and why they're kind of sparse. And also I improved in analyzing code, so I learned how to think starting with high-level interactions and components, and then working my way down to individual functions, bugs, and errors that I needed to fix. For some more general learnings, I learned how to break larger goals into manageable tasks. So of course, this was a really large project. So learning how to break this into smaller, realistic goals and make progress each week was a great learning experience that I'll definitely carry with me. And lastly, I learned how to collaborate and communicate more effectively in a technical setting, from asking for advice and feedback to communicating my progress with my mentor. So my mentor, Peter, was really great about helping me understand why certain parts in my code weren't working and the fundamentals behind concepts in C++ and multi-threading. So this really gave me the tools to unstick myself in the future and make my progress more efficient later on. So I'm really thankful for his help and dedication throughout this. And lastly, I learned how to give technical demos in a more improved way, like this presentation. It's very new to me, so I'm very thankful for the opportunity to present my project to everyone. Thank you so much for listening to my presentation. If you are interested in this project and would like to learn more, I have some documentation at the wiki page link below for the Parallelized Parsing project, and I'd be happy to answer any questions.
Did Peter get a chance to discuss the two buffer approach we were thinking about for shaking out the overhead?
Yeah, we talked about it this week. Yeah, it seems really interesting.
Seems promising. It seems like if we can get that working, then plausibly leave and improve on just what's already there, even with just a single parsing thread. And if we can, and then of course, you'll have no overhead associated with going into even more threads.
Mm-hmm.
I have a question. Was all your testing on like a laptop type machine, or did you try anything on a machine that has high I/O bandwidth?
I just tried it on my laptop since that was what was available, but yeah. Okay.
We did some testing around this, and there's a big difference between like a maybe Peter's machine at work and like a laptop. So it might be worth trying.
Yeah, I'd be curious to see with different classes of hardware how this changes. I imagine there'd be a fair amount of difference. It's really interesting to see the plateau and then sudden drop at, what was that, 7 threads? Kind of makes sense with eight threads of execution on the machine, but yeah, it's interesting to see.
Yeah, we're thinking some of the plateau in like the middle threads is also due to the high variance in file I/O. But after 8 threads, at least on my machine, which has 4 physical cores and 8 logical cores. After 8 threads, we really see a plateau from there.
I have another question. Is there a way to just test parsing by itself without the ML component? So assuming like someone really drinks the queue really fast on the other side.
Yeah, so there should be like 2 ways to approach this. First, there's a test in the testing suite called parser throughput, which is kind of a work in progress for like the new implementation for the parser, but basically you can use that to just test the parser. You could also create like a no-op implementation of the learner and then just test the parsing component where the examples aren't really being used by the learner.
Cool, thanks.
Do we have any more questions? Okay. Thank you so much, Cassandra.
Thank you.
We have Mark next, who is working with Paul, I believe, on a modern benchmarking package for reproducible contextual bandit research.
Yeah. Hi, everybody. Can you all hear me? Is my mic on okay?
Yep.
Great, great. Let me share my screen here. Everything coming through?
Yep, looks good.
Okay, great. Nope, that's the wrong button. That's the button. All right. Well, thank you, Jack, for the introduction. You said I'm going to be presenting today about the Reinforcement Learning Open Source Fest benchmarks and competitions project. A little bit about myself to start with. My name is Mark Rucker. I'm a third-year PhD student at the University of Virginia, where I do research with inverse reinforcement learning models, trying to do interventions to change people's behavior around healthcare practices. My mentor this summer was Paul, and he really helped me a lot with this project, gave me a lot of vision and direction when I come at him with a lot of ideas. So I owe him a lot of credit for what you're about to see. So before we get started, I want to talk a little bit about benchmarking. I don't know who all in this meeting has done benchmarking before. If you have, I'm sorry. I imagine you're going to understand what I'm talking about. And if you haven't, I'm going to try to explain it to you in a way that makes sense. So benchmarking is hard, it's tedious, and it's questionable. Not questionable as in, should we be doing this? But questionable as in, if you ever show somebody the results of a benchmark you did, the first thing they're going to say is, are you sure? And given the amount of time and effort benchmarking takes, this makes the whole process kind of discouraging and not a lot of fun to do. The reason I think for this and the big challenge that I was fighting against this summer and what drove this project is you can think of benchmarking as rolling a die. When we write code, we're able to test by hand, usually at best, maybe a couple hundred, couple thousand if you test a lot, states of the program. Though there are likely maybe 1 in 10,000 states that still can lead to catastrophic failure. So if we have 1 in 10,000 odds of our entire program crashing to the ground, and we want to now take a couple 100 million observations and run it through our program where we're using algorithms that are likely using random generated behavior, there's a really good chance you're going to hit that 1 in 10,000 failure state. And when you do, it's going to be really hard to know what happened. So what we set out to do this summer is to create something that takes all that difficulty, all that problem a way so that researchers in the contextual bandit community can focus on research and productive avenues forward instead of fighting for problems and implementation difficulties. So our COBA benchmarking has 4 things that we're really proud of. 1, we worked really hard to make it really easy to add new data sets, which I hope you'll see as we go. 2, we worked really hard to make it really easy to add new algorithms in a field of research that's growing as quickly as contextual bandit is, both in terms of data sets and algorithms. That seemed necessary for the field. And then finally, we worked really hard to make it easy to create new benchmarks from scratch and then to share those benchmarks with other people. As I mentioned, the field of contextual bandit research at this time is on a pretty rapid growth trajectory. What you see here, and these numbers are small, but this bottom right starts at 2009, which was 1 year after John's Langford's seminal paper on contextual bandits in 2008, and we've just seen a growth since then. This last year is 2020, and I'm only assuming that this will grow even more, barring COVID having some kind of an effect this year. So along with the field of contextual bandit growing, there's also a growing focus on reproducibility within AI and machine learning in general. You see it in industry, you see it in research, all across the board, and you see it in science journal writings as well, professional writers. So taking all these things together, we felt like this summer was a really great chance for us to put our flag in the sand and maybe do something that could really guide the direction and the future of this field in a meaningful and positive way. So we present to you, or I present to you right now, COBA, which is an acronym from Contextual Bandit. And what I hope you walk away from this presentation in the next 5 to 10 minutes is that COBA has good bones. I've worked on it for the last 3 months, blood, sweat, and tears. It's got some rough edges still, given that it was a 3-month period, but I think it has a really strong foundation and core, which was important in my mind for an open source project to grow beyond myself in the future. So what is COBA? What you see here is a quick high-level architecture of COBA. But before we get to that, I want to take you over to our GitHub page, where we have some documentation. There's some room for improvement here, but just so you all know what's out there, and I hope to add to this in the coming days. COBA, an agile collaborative benchmarking framework for contextual bandit research, the COBA way. So these are some of the things that I think really make this package stand out from the crowd. We designed this package to be lightweight. It has no dependencies on outside third-party packages to get started. For some of the more advanced functionality, for example, Valpal Rabbit, you have to install packages, and if you try to use that functionality, we direct people to those packages at that time and tell them how to use them. COBA is distributed. We built it with web technology up front from the ground up, and so it is made to work across HTTP from devices. It has caching to preserve server requests and save on bandwidth. It supports separate API keys and configuration files for web APIs, as well as MD5 checksums to make sure everything comes in right from the network. It is verbose. It has a highly functional, highly customizable logging framework, which is important when you're running your 100 million attempts at your 1 in 10,000 failure dice. When it does fail, you want to know why, where, and when, and how, so you can fix it. It's robust. It takes 9 hours for me to run our longest benchmark that we created on my machine. And so given that time, if my computer went down, if the program crashed or anything, having to restart after 8 hours into a 9-hour job was a lot of lost work. So it writes every single action during the course of the benchmark to file, and you can always resume immediately exactly where you left off, losing at most 5 to 10 minutes of work in the case of a system crash. It is just in time. We built this from the ground up in a lazy and deferred mindset. My laptop has, in theory, 8 gigabytes of RAM, but between the Windows operating system and the virtual Linux machine that I run for my development, I have about 4 gigabytes of RAM available to me at any one time for program use. That means I had to load files and use them and then unload them immediately. That kept the entire program very lightweight and with no memory leaks. And then finally, COBA is a duck. We make heavy use of interfaces to make it easy to extend COBA, but we never expect inheritance. All of our interface usage follows duck typing so that people can extend and build on COBA without actually having to directly deal with our type hierarchy themselves, unless they want to. There are benefits to it, but they don't have to. So to give you a quick rundown of what these interfaces look like, we have 3 interfaces for the COBA architecture. The first one we call a simulation. Simulations are what are your data sets, and it's a sequence of interactions where an interaction is defined as a context, the actions you can take in that context, and then a key uniquely identifying that interaction for reward lookup purposes. Next, we have our algorithm interface. We also wanted to keep this very simple. The only thing that's necessary to implement here is the ability to choose given a context and actions along with a key, and then to learn from that. Once you make a choice, we then pass the rewards back.
You have about 5 minutes left.
Thank you. And then finally, the benchmark configuration files, which is how we make benchmarks customizable and shareable. Benchmark configuration files are JSON files with a templating engine. So what you see up top here is a template that I made that I called shuffled OpenML classification. I have my random seed so that this is totally reproducible. I tell it what type of data set it is, and I tell it where to fetch it from the web. I then define 3 data sets down here using my template, OpenML set 3, 6, and 8. And the final architecture, as I mentioned already, has this layout. You have a Python package that we build. This is COBA with learner simulations benchmarks. The website portion, which unfortunately this summer we did not get to, but we have plans to continue to work on that as this semester progresses. And then OpenML, which at this time is our only remote data store, but the framework and architecture is there to read from any REST API. And hopefully in the future, when people use this, then they'll be implementing their own learners and running on their own client machine, keeping us out of the processing world. So a real quick example of what COBA looks like in practice. This has been published to PyPy. If you look at this and think, hey, I want to go play with this today, you can find it at, just do a search for COBA. And we are at version 1.01. So you can download this now. That's what I'm actually using. And so here I import my benchmark, my learners that I want to test, some utility methods that we made to create nice and easy plots. And this is actually no longer needed. That's old code. So I define my learners that I want to test. These are built, and we have plans to extend these and continue to add to these. You'll hopefully notice a lot of ones that you all likely know. So we have a random learner that just randomly picks as a baseline, epsilon learner, UCB, and then many Valpal Rabbit search algorithms. It supports both ADF and non-ADF in the same interface. So for example, this says ADF by default, but I can make this, and this will now run epsilon greedy search on non-ADF Valpal Rabbit. Here is what it looks like to run a benchmark file. So the first thing I do is I tell it to load that JSON config that I showed you earlier. Next, we tell it to evaluate the learners. And this is where it writes the transactions every single line so we can resume. And when it gets done, I tell it to write all the results of everything you just made to result.json. I can load my results. And here you can see, I'm going to just see what my results look like. And I see, OK, my results, I have 8 learners in here. I have 438 simulations. And I have 173,191 batches within this result set. So I can plot it real quick. And down here, you can see all my learners. They have their names as well as their parameters used. And we see some odd behavior. For example, all these are very flat, and this seems to get worse. What's happening here is that we're weighting. And so a few really large data sets are biasing things to make it look uneven. When we tell it to not weight by the size of the data set, we see this learning curve, more like what we would expect. So we can drill down and see what's inside the results, and we can tell it to turn the results into pandas. And we can see our learner table, our simulation table, and our batch table. We can continue to drill down and take this apart, but I think that's my time. So I hope this gets you excited. I'm really proud of what we built this summer, and I look forward to continuing to work on it. I learned an incredible amount about Python type systems and unit testing. I'd never worked in Python on a project this scale, so everything is using, these aren't good examples, type inferences, so generic types, type vars, things like that, return types. So thank you guys for this opportunity to test out my chops and do something new. It was a lot of fun.
Thanks, Mark. We can open it up to questions or comments.
This seems great. Did you have a chance to play with it on mini data sets and get a sense of different exploration algorithms and how well they work?
You know, we were just getting to that phase, to be real honest with you. And that's what we hope to do next. I have plans. I've talked to some people on trying to find a good benchmark set of data sets and begin to implement more algorithms. Yeah. So what you see here, there was a paper published this summer from your group, or last year, the contextual bandit bake-off paper.
Yeah.
This data set that I have read in here and processed are all the OpenML IDs from that contextual bandit bake-off paper, which is about 520 or so. And so that's what you see here. So here's a real quick example of what that looks like at a high level. UCB on this across the board with no other qualifications seems to do best. But when you start to drill down, it's just like some smaller data sets. And I didn't do any hyperparameter tuning. Because like I said, it takes me about 9 hours to run this. And so I hadn't had time to do the hyperparameter tuning yet, which is really what we want to know. And so you can see here the learners. When I implement the learner, I have what's here, the family, as well as the hyperparameters. So when this is all done, once I put in more learners, you'll be able to like say, okay, give me this family. Let me look at the VW bag family and what hyperparameters seem to do best when we don't know anything about the incoming data set. Which may or may not be useful since you usually know the data set you're working with, but it's kind of fun. Yeah, so we're just getting to that phase and where some of the really exciting fun stuff's happening.
Cool. Other questions?
I have a question. If we have time, can you just highlight the shareable part, or just like what you created for the sharing the results?
Yeah. So I mean, right at this time, when I say shareable, it's this config file. So for example, what you see here, I could, if you had this package already installed on your own personal machine, I could send to you this file right here that has the benchmark that I'm running all those algorithms against in a repeatable fashion. We're in the process of also being able to include the actual learners in here in some kind of like a pickle format or something, so the whole thing is repeatable. But we're not there yet. So right now it's just the benchmark.
Perfect. Thank you so much. Great work.
Thank you. And we hope to put shareable like results on the web too, a website where you can maybe see who's the best performer. We started on that. I'll just show you a little bit. Here it is. It has nothing on it yet, but it's in the works.
We should, Mark, we should link this to the Valpal Wabbit website as well.
Yeah, so we're already on a repo in the Valpal Rabbit organization, but okay. I definitely need to add more feedback, probably to your sites from this project. It's been on my to-do list, yeah.
Okay, great. So, hey, Mark and Newton and Cassandra, thank you so much. Awesome presentation, awesome work. It was a pleasure hosting you this summer. I hope you had as much fun as your mentors had, you know, just working with you. And with that, maybe we finish at 12 so people can go back to whatever meetings they have at 12 o'clock Eastern. So John, you can stop the recording and we'll share it.
Yeah, I'll do that. Newton, Cassandra, and Mark, just thank you for all the work you did this summer.
Thank you. Yeah, thank you guys again.
Thank you. Great work.
Yeah,
Okay.
thank you so much. It's been a pleasure working with all of you guys. And don't, like I said in the email I sent around, don't be afraid to stay involved. Yeah.
Indeed. Okay, everybody. Thank you all.